Let's talk about hybridization of orbitals. Hybridization means orbital mixing. So there are 5 types of hybridization we can discuss: sp hybridization and sp2 hybridization, sp3 hybridization, sp3d hybridization, and sp3d2 hybridization. So this meaning is sp, s orbital and the p orbital mix together. How many orbitals mix? 1, 2. 2 orbitals mix to make 2 sp hybridized orbitals. Number of orbitals mix is equal to the number of orbitals formed, hybridized orbitals formed. This is 1s orbital mixed with 1 p orbital to make 2 sp orbitals. And sp2 hybridized orbital meaning is 1s orbital mixed with 2 p orbitals. That is, we got sp2. So this sp3 meaning is s orbital mixed with 3 p orbitals. sp3d means s orbital mixed with 3 p orbitals and 1 d orbital. sp3d2 means the same way, s orbital mixed with 3 p orbitals plus 2 d orbitals. Now let's see how many orbitals are formed. Two orbitals mix, s and p. So 2 orbitals mix to form 2 hybridized orbitals. sp2, 1s and 2p's. 3 orbitals are mixing together form 3 hybridized orbitals. In sp3, 1s and 3p's. So 4 orbitals are mixed together to make 4 hybridized orbitals. And sp3d, so 5 orbitals are mixed together to make 5 hybridized orbitals. And sp3d2, 6 orbitals are mixed together to make 6 hybridized orbitals. Now you can clearly see what are the 5 types of hybridization, what are the meaning of sp to sp3d2 hybridization. Now another important thing before we move on to hybridization is what are the shapes of the orbitals. So s orbitals, we all know all s orbitals are spherical shape like spheres, and p orbitals are dumbbell shape, 2 lobes like a dumbbell. So s and p orbitals, spherical shape and the dumbbell shape orbitals, if we mix together, if we join together, it makes hybridized orbitals. So these hybridized orbitals have same shape. So initially for sp hybridization, s is spherical shape, p is dumbbell shape. But after we mix these two, we can make two identical, two same type of sp hybridized orbital. So sp hybridized orbital looks like one side has a large lobe, the other side having a small lobe. And the same for the other hybridized orbitals. One lobe is large, one side lobe is large, and the other side lobe is small. But initially, before hybridization, we have spherical shapes, s orbitals, and dumbbell shaped p orbitals, different shapes. But if we mix together, we can make same shape of the orbitals. Now let's move on to hybridization. Now you can clearly see sp hybridization. So it is related to the two bonds containing molecules like BeCl2, beryllium chloride. And sp2 means 3 hybridized orbitals can overlap with 3 atomic orbitals to make trigonal planar geometry like Bf3, BCl3. And 4 means we can make 4 bonds, 4 hybridized orbitals overlap with 4 atomic orbitals. It's like tetrahedral geometry and like CH4 methane. So 5 hybridized orbital means there are 5 hybridized orbitals that can overlap with another 5 atomic orbitals. So it can form 5 bonds like PCl5, trigonal bipyramidal geometry. Next one, sp3d2, there are 6 hybridized orbitals can overlap with 6 atomic orbitals can form octahedral geometry. So I will quickly go through this, the linear shape and 3 trigonal planar, and this is tetrahedral and trigonal bipyramidal, and 6 bonds we can make in octahedral. Right. Now you will have an introduction, the idea about hybridization or orbital mixing. Now let's move on to sp2, sp3 hybridization, how we can explain the shapes of the molecules, linear, trigonal planar and the tetrahedral. Let's talk about sp hybridization first. sp hybridization. sp hybridization, S and p orbitals, spherical shape S and dumbbell shape p orbital mix to form 2 sp hybridized orbitals. Example, let's pick BeCl2, beryllium chloride. For BeCl2 is a linear molecule. If you draw a Lewis structure, it looks like this. Be is having 2 BeCl bonds. Be is the central atom. So here you need to find out the central atom in the Lewis structure before you move on to hybridization. So beryllium is our central atom. So beryllium atomic number is 4. Let's write the beryllium electron configuration. 1s2, 2s2 is a configuration. So if you draw orbital diagram for 1s2 and this is 2s2, and in the valence shell, that is outermost shell, is shell number 2. This is 1s, 2s and 2p, and this is for beryllium. So first we draw the Lewis structure. From the Lewis structure we can identify what is the central atom, that is beryllium. So beryllium configuration is 1s2, 2s2. In the Lewis structure it looks like this: 1s2, 2s2, and in the n is equal to level there are p level also available, but p level no electrons. This is how the beryllium atom looks like. Now after you draw this orbital diagram, you need to identify what is the valence shell. Valence shell means outermost shell. So here valence shell is shell number 2. In shell number 2, s orbital and p orbitals are available. S orbital is 2 electrons occupied, p orbitals no electrons here. That is our first step. Our second step is electron promotion in the valence shell. Now we don't need inner shell, the 1s shell, we need only the outermost shell or valence shell. So let's write valence shell again here. 2s, and in the 2p level there are 3 p orbitals without electrons. Now we are doing the second step is promotion. We call electron promoted to the next highest level. So one of the electron in the 2s orbital, now we promoted, or we draw the electron in the next highest energy level, that is 2p level. So after electron promotion, the orbital diagram looks like this. One 2s orbital we promoted to the next highest energy level. Now we have one electron in the s orbital, one electron in the p orbital. That is our second step. Our third step is, now after we promote these electrons, let's mix these two orbitals. because we need to form only two bonds, BeCl, two bonds. So central atom form two bonds means we need to mix two orbitals. So let's mix two s and two p orbitals together. Next step is mixing of the atomic orbitals. This is 2s, one electron in 2p we mix together, and the remaining 2p orbitals are here without electrons. Right. So if we mix these s and p orbitals together, we can make equal the size and the shape 2sp hybridized orbitals, each hybridized orbitals having one electron, and the remaining 2p atomic orbitals are available like this. Now let's go through the steps again. The first step is we draw the Lewis structure of the given molecule BeCl2, and then we identify what is the central atom. For the central atom, we write the electron configuration 1s2, 2s2, and then we draw orbital diagram. We need only the valency shell. So let's pick valency shell 2s2, 2p. So from the valency shell, next step, electron promoted, one of the low energy electron promoted to the next highest level. So S is the lowest occupied level. So we promote one of the S level electron to the P level. That is our second step, electron promotion. And the next one is we need to make two bonds. So let's mix two orbitals, S and P. So after we mix two orbitals, it makes two hybridized orbitals. They are same shape. Initially we have a spherical shape S orbital and dumbbell shape p orbitals. But after we mix, we have the one lobe large and one lobe small, same size of S p orbitals, and the remaining 2p atomic orbitals are here. Now these are hybridized orbitals and these two are atomic orbitals. Now let's see how we can make a bond. Now we have sp hybridized orbital. Beryllium is here. On beryllium atom we have two hybridized orbitals. So the one lobe large and one lobe small. Right. This beryllium. Now let's see chlorine. Chlorine electron configuration, outermost configuration is 3s2 3p5. So we need only the chlorine's outermost electron configuration. So if we draw the orbital diagram, it looks like this. S level 2 electrons and p level 1 2 3. There are 3 p orbitals, 2 lone pairs and 1 singly occupied electron. This is how the terminal atom looks like. Terminal atom valence shell looks like. So now these hybridized sp orbitals overlap with the singly occupied 3p orbital of the chlorine. So p orbital is normally dumbbell shape. So chlorine's 3p orbital is a dumbbell shape. Looks like this. This is chlorine. Right. That's how the beryllium is forming BeCl, two BeCl bonds. So let's name again. Beryllium form two sp hybridized orbitals, and the terminal chlorine atoms 3p orbitals, 3p atomic orbitals come and overlap with two hybridized orbitals on the beryllium in each side, forming BeCl2 linear molecule. So then bond angle is 180 degrees. This is how sp hybridization is going on for the linear shape molecules with single bonds. Hope you will understand sp hybridization. Let's quickly go through sp2 and sp3 with examples. Next step is sp2 hybridization. S sp2. So sp2 hybridization, there are three orbitals mixed, 1s and 2p's. I will pick trigonal planar geometry because there are three bonds we can form. Trigonal planar geometry looks like this, like all the atoms on the plane, on planar geometry, BF3, BCl3, formaldehyde examples. So let's pick boron. So boron is our central atom. The configuration is 1s2, 2s2, 2p1. So if you pick a valence shell, that is 2s2, 2p1, let's draw the configuration orbital diagram. Only one p orbital occupied here. The other two are empty. That is the valence shell. So our next step is promotion electron. So I will indicate with star, that means the electron promotion. So lowest energy occupied electron we promoted to the next highest level. That means one of the 2s electron promoted to the one of the p empty p level. Now it looks like this after promotion. So s level electron go to the next highest energy level. So after electron promotion, we need to mix orbitals. So how many orbitals in sp2? 1s mixed with 2p orbitals. So let's mix 1s and 2 singly occupied orbitals. And then after mixing, it form 3 hybridized orbitals. Each occupied 1 electron. These are sp2 hybridized orbitals. And the remaining p orbital, remaining atomic p orbital looks like this without electrons. Now let's draw the beryllium molecular, boron molecule again. Boron. So boron is having one large lobe, small lobe, and this side one small lobe, large lobe. The same way, the hybridized, three hybridized orbitals are on the boron. Like this. These are sp2 hybridized orbitals. Now we need to form 3 BF bonds. How? The fluorine molecule atom electron configuration in the valence shell. Electron configuration in the valence shell for the fluorine is 2s2, 2p5. It looks like this. In the p level, 2 paired electrons and one unpaired electron. This is 2p and this is 2s. So fluorine atom singly occupied 2p atomic orbital, those are dumbbell shape, come and join with each of these sp2 hybridized orbitals to form 3 BF bonds. This is how the BF3 bond looks like. 1, 2 and 3. So these are 2 p orbitals of the fluorine, and on the boron there are sp2 orbitals, 3 sp2 hybridized orbitals. Right. Now you will understand sp2 hybridization. Write the configuration of the valence shell, electron promotion, and then orbital mixing. And after we make the hybridized orbitals, we need to overlap hybridized orbitals with atomic orbitals of the terminal atoms. Let's quickly go through sp3 hybridized orbitals with examples. So I'll pick sp3 hybridized orbitals. Example, methane CH4 sp3. Example CH4. We called methane. CH4 Lewis structure looks like this. The actual structure looks like wedge and dash. One bond is coming out of the paper, one bond is going inside the paper, but I will simply draw like this, CH4. Now there are 4 bonds. sp3 hybridization means there are 4 orbitals we need to mix, 1s orbital and 3p orbitals. So let's pick the central atom carbon. So carbon electron configuration is 1s2, 2s2, 2p2. So valence shell here is again shell number 2, 2s2, 2p2. So it looks like this. 2 electrons in 2s level, and in the 2p level there are two singly occupied electrons. The other orbital is empty. So let's quickly go through the step promotion step. One of the electron in the 2s low energy level promoted to the next highest energy level. Then 2s orbital, 1 electron, and all 3p orbitals now occupied with 3 single electrons. So after electron promotion, our next step is orbital mixing. Now let's mix all 4 orbitals, 1s and 3p orbitals together. It looks like same shape and the same size. 4 sp3 hybridized orbitals are formed now, each having 1 electron. These are 4 sp3 hybridized orbitals. So why 4 hybridized orbitals? We mix 1s and 3p's. So number of orbital mix is equal to the number of hybridized orbitals formed. Now if we draw the carbon is our central atom. There are 4 hybridized orbitals on carbon, like this. So these sp3 hybridized orbitals needs to form overlap with hydrogen is our terminal atom in CH4. Hydrogen is having only s orbital. So hydrogen 1s orbital come and overlap with the sp3 orbital of the carbon, making 4 CH bonds. This is how the CH4 bonds are formed. This is 109.5 degree bond angle with tetrahedral geometry. 4 bonds and 0 lone pairs according to VSEPR theory, tetrahedral. I hope you all understand now what is the meaning of hybridization, what are the steps we can find out the hybridization. Okay, thank you so much for watching. If this video is helpful, please subscribe and share with your friends. And if you need any other topics to discuss, please comment in the comment section. Thanks.